Okay, now we're going to take a look at the derivative involving inverses. Derivatives involving inverse is kind of a ugly looking expression here. The whole idea is that you don't know what the inverse function is. You typically only know the original function f, but you don't know the inverse function g. However, you know some values of the function and its inverse. So in order to find the derivative of an inverse at a function, it's equal to 1 over the derivative of the original function f of g of whatever this number is here. Sounds kind of ugly, but it's really not that bad. I just want to show where this derivative definition comes from using compositions of functions, and then we'll look at a couple examples. So first off, I'm just going to let f of g of x equal f of g of x. Well, this is a composition of a function and its inverse, and this is the same thing. So this side over here, I'm just going to let this be equal to x, because when you take a function and compose it with its inverse, you get whatever your input value is, which in this case is x. So I'm just going to rewrite the left-hand side. So I really haven't done anything other than use the properties of functions and inverses. I'm going to take the derivative of both sides. So I'm going to differentiate this side and differentiate this side. Well, this is a chain rule situation here, where derivative of the outside, so f prime of g of x, times the derivative of the inside, which is g prime of x, so that's just chain rule, that's chain rule definition, is equal to, well, the dx over dx is just equal to 1. So if I solve for the derivative of the inverse, this piece gets thrown over there, so I get g prime of x is equal to 1 over f prime of g of x, where f and g are inverses of each other, so the derivative at some value x of the inverse is equal to the derivative of the function of the inverse function at a value. So let's look at a couple examples. Okay, so we have a function. Here's our original function f. We want to find the value of f of the inverse of x when x is equal to 3. So we want to find the inverse value when x is equal to 3, and then find the derivative at x equals 3. So another way to look at this is g of x, so this is the inverse when x is equal to 3. So we really want to know what is g of 3. And then this is the inverse derivative, so this is what is g prime of 3 equal to, because when x is equal to 3. So the first thing we need to know is what is g of 3. Well, if it's an input of g in inverses, that means it must be an output of f. So therefore 3 must equal 1/4 x cubed plus x minus 1. So this function, the original function f, is going to equal 3, because 3 is an input of g, so it must be an output of f. So we just have a cubic function here, so I'm going to move 3 over. So I get 0 equals 1/4 x cubed plus x minus 4. And using my graphing calculator, I figured out that x is equal to 2. So again, our definition of finding the derivative of an inverse, it's equal to 1 over f prime, the derivative of the function f at g, which in this case is 3, is going to be equal to g prime of 3. So what do we need to know? We need to know what g of 3 is equal to. Well, we just figured out g of 3. G of 3 is equal to 2. So g of 3 is equal to 2. We just need to know what f prime is. So f prime of x is up here is 3/4 x squared plus 1. So using this expression here, g prime of 3 is equal to 1 over f prime of g of 3. We determined g of 3 is 2. So g prime of 3 is equal to 1 over f prime of 2. So therefore, really, the derivative at 3 of g is equal to 1 over the derivative of f at 2. So let's plug 2 into our f function here. So f prime of 2 is equal to 3/4 2 squared plus 1. So this is equal to 3/4 times 4 plus 1, which is 3 plus 1, which is equal to 4. So therefore, g prime of 3 is equal to f prime of 2, we just determined is 4. So it's equal to 1/4. So again, we have f as our original function. We want to find the derivative of the inverse. So this is really g prime of a, where a is equal to a half. So really what we want to know is what is g of a half is equal to what? And then our definition of g prime of 1/2 is equal to 1 over the derivative of the original function of g of 1/2. Well, first we need to figure out what g of a half is. Well, we're given the the original function f. So if it's an input of the inverse, it's an output of the original function. So 1/2 equals the sine of x. When is sine of x equal to a half? Well, that's going to be equal to pi over 6 and 5 pi over 6. For some reason, this problem is only defined over the first and fourth quadrant, so we only want the pi over 6 value. So that means g of a half is equal to pi over 6. We also need to know what the derivative of f is, so f prime of x is cosine of x. So g prime of a half is equal to 1 over f prime of g of a half, we just determined is pi over 6. So we need to know f prime of pi over 6. So f prime of pi over 6 is equal to the cosine of pi over 6, which I believe that is equal to radical 3 over 2. So that means g prime of a half is equal to 1 over radical 3 over 2, which this is just reciprocated, so it's 2 over radical 3. So as long as you're able to memorize this definition right here and know that the input of an inverse is the output of the original function, and how to find the derivative, it's really not that bad. The hardest part is just memorizing or keeping this fresh in your mind. The easiest way I find to do it is to just know that f of g of x is equal to f of g of x. This is a composition of functions, so I get x, and then this is f of g of x. And then using the chain rule, I can take the derivative, which is f prime of g of x times g prime of x equals 1, and then just solve. And then just solve for g prime of x, so therefore this piece over here gets thrown underneath, and then that's how it is. That's just how I remember it. I don't memorize this rule right here. I memorize that f of g of x is equal to f of g of x. This is x, and then differentiate both sides using the chain rule, and it comes out to be not that bad. Got one more example. Okay, here's a classic AP exam problem. You're given a function f of g or inverses, and you're looking to find f prime of 6. So we know g prime of 3, we know f of 3, and we know f of 6. So we need to know f prime of 6. So in this case, the original function is g, and f is the inverse. So the reason I say it that way is because now I want to write it as g of f of x is equal to g of f of x. Because I want to end up taking the derivative of f, I want to solve for that. So again, the right-hand side is a composition of two functions. You just get x. Using the chain rule on the left-hand side, I get g prime of f of x times f prime of x. Now, if I solve for f prime of x, I'll be able to determine the derivative of f prime of x. Well, f prime of x, oops, I was supposed to take the derivative of x there. That should have been 1. So solving for f prime of x, I get 1 over g prime of f of x. So we're looking for f prime of 6. So wherever I see x, I put 6. So I get 1 over g prime of f of 6. Well, we know f of 6 is equal to 3. So we get f prime of 6 is equal to 1 over g prime f of 6 is 3. And how convenient. We know g prime of 3 is 4. So we get f prime of 6 is equal to 1/4. Okay, so just as long as you're able to recognize which function you're trying to take the derivative of, makes it easier to set up this initial relationship and then solve for the appropriate derivative you want and then plug in the applicable values. Okay, that's the end of inverse derivatives involving inverses.